All right, it's 8 o'clock, so let's get started. This is Games with Go episode 15, where we're going to finish up our exploding balloon game, and then we're going to start talking about the next project, which will be the evolving picture project. So we have at least some people that are here instead of watching the Super Bowl, so that's great. Probably a lot of people will be tuning in after the Super Bowl. So last episode, we started getting the explosion animation working, but we had a bug where if you click and there's multiple balloons under your mouse, all of them start animating the explosion. And the other thing we need to do is we need to actually delete the balloon, remove it once the explosion's done. Right now it stays alive. So the reason this is tricky is we're using a common game programming pattern where we iterate over all the entities in our game, which in this case is just balloons, and we call update on each entity. And this is a nice way to work with things that people are comfortable thinking about, where each entity takes care of updating itself and each entity takes care of drawing itself. And a lot of game engines set things up for you this way, but it's not always the best way to do things. And in this case, the problem is a balloon by itself doesn't know if it is the frontmost balloon or not. And we only want the frontmost balloon to blow up if it gets clicked on. So let's change this around a little bit. Let's make the update function for balloons. Instead of operating on one balloon, let's have it operate on all the balloons. So we're not going to make this a balloon receiver function anymore. And we're going to call it update balloons. And we're going to pass it all the balloons. And then in here, we'll do our loop. And that'll just wrap around everything. And what we're going to want to do actually is our balloons are currently sorted so that the furthest away balloon is drawn first and the closer ones are drawn after. And that guarantees that the closest balloons are drawn on top of the ones farthest away. But for checking which one to explode, we actually want to get the closest one first and then stop checking for click events. So we're going to actually want to go backwards. So instead of this, we're going to do this. We're going to start at the length of the balloons array, go until we hit 0, and count down. And all of this can be pulled out of the loop. All right, then to get the current balloon, get balloons of I. Okay, so here is where we're checking to see if a balloon got clicked on. So what we want to do is set up a Boolean to see if a balloon has been clicked yet. Started out equal to false. If one does get clicked, we set it equal to true. And then if a balloon's been clicked, we don't want to check anymore because we're only going to let you click one balloon at a time. So we say if not balloon clicked, and otherwise keep it the same. So in order to check if a balloon has been clicked, we only let one happen, because as soon as you get into this loop, if the click was within the radius of a balloon, then balloon click is set to true. We play the sound and start firing off the exploding animation. All right, and then another thing we want to do is we want to remove a balloon from the list if it's been exploded, so we don't draw it anymore. Now, one thing we could just do is check to see if a balloon's exploded, and then not do anything in the draw loop. And that'll work fine, but it would be nicer to actually shrink the list so we can use less memory as the balloons count down. We don't need to do this with a game this simple, but it'll be a good exercise. So let's keep track if any balloons have exploded. So balloons exploded, we'll set that equal to false. And then here, if a balloon has exploded in this update loop, we'll set balloons exploded equal to true. Now, once the loop is done, we can go about removing the balloon or any balloons that have exploded from the list. You could do this inside this loop, but it is tricky. So we're not going to get that complicated today. So instead, we're going to check here to see if any balloons have exploded. Because if they have not, we don't want to bother removing anything from the array. Okay, so now we're going to learn a trick with slices. So we're going to make a new slice, filtered balloons. And that is going to point at our balloons array at the very start of it. Okay, so at this point, filtered balloons is an array or a slice with 0 things in it, but it starts at the same place that our current balloons array starts. Then we will iterate through the existing balloon slice. And if the balloon has not exploded, we will add it to the filtered balloons. Okay, so what we're doing here is we're changing the array in place. So you could imagine we have an array of balloons, balloon, balloon, exploded balloon, balloon. And what you could do is just make a whole new slice, right? And then copy balloon, skip this, copy balloon. And then this, this array would get garbage collected and we'd start using this slice. That's fine, but if we want to avoid that garbage collection so that we avoid garbage collection pauses, which can be important in games as they get more complex, then we can do this in place, right? So in this case, our filter balloons is pointing to the same memory. So as we update, right, this just gets copied onto itself. This gets copied onto itself. And we get here, and we don't add anything to the filtered array. So the filtered array is still pointing here. And we count up to the next element in the balloon array, and then we copy this B over to here, and then that's our new slice. In the same place, in the same chunk of memory, so that we're not having to allocate new memory and garbage collect the old memory. If there's any questions about that, I know it's a little confusing, fire away in chat. So once this is all done, we'll set balloons equal to filtered balloons so that this name now refers to the slice that's been shortened. And then we're going to need to return that so the main loop knows about it. So we'll have to update our function definition to return a slice of balloons. Then we'll go way down here, and instead of looping through, we call update balloons with our balloon slice. Right, so we have to set our balloon slice equal to the what is returned from here in case some balloons got exploded, so that they get removed from the array. And, oh, not is equal to. All right, let's give it a try. Ooh, we have an error. 109. Let's see. Oh, this should be length of balloons minus 1 because it's an array-based, zero-based array. Nope, we died. So all the balloons disappeared. That probably means something went wrong here. Okay, I think what's happening is we're setting balloon exploded to false the first time through this loop. We only want to do this check if a balloon is currently animating the explosion. So if the balloon's exploding, check to see if it's done. All right. There we go. And we've done it. We've killed our balloons. Okay, so this gives you a good sort of template or basis for doing some easy or basic 2D games. You could easily turn this into a car driving game or a platformer. You've got the ability to draw textures and scale them and move them around. You've got a basic vector library for doing some basic physics and some ideas for how to use a game loop and update and draw things. So last week I gave a homework for trying out insertion sort. And if you haven't done that, I still strongly recommend it. It's like a really good thing to practice to see if you can get this working on your own and make it perform well. If you can get close to or beat Go's built-in sort, that would be, you should consider that a success. I'm going to give another homework for today. Currently, our balloons just kind of float around. I mean, one goes in front of another, it just pops in front, right? It's not, they're not colliding with each other or bouncing around like real balloons would. So homework number 2 will be to do some basic collision detection and have the balloons bounce off each other. So implement collisions. And so some tips here, I would treat the balloons as a sphere, which means to check for collisions, you only have to check distance. Right, and if the distance is less than the radius of a balloon, you know they've touched. And something else you'll need to keep in mind. Oh, and you can use, you know, we've already got the vector3 library function for computing distance, so you can use that. And then there's another idea you want to keep in mind. Yeah, so there's an idea called the minimum translation vector, and we talked about this a little bit when we did Pong. You'll need to keep this in mind, because when things collide, they are not guaranteed to just collide exactly. Right? When one balloon collides with another, it could overlap a little bit, such that if you change their direction once they've collided, you make them bounce away, it's possible that on the next frame, they're still touching, maybe touching less, but still touching. And then you might reverse their directions again. Right? That would be the naive code, is just reverse directions whenever balloons collide. And you can see here how they can get to where they're stuck, colliding forever. So when you have a collision, you need to see how far apart they are and figure out how far apart you need to move them so they're no longer touching before you reverse the direction. And that concept is called minimum translation vector. Since we're treating them as spheres, that's not too complicated. And so you can Google this to read up on more. So getting this working really well is hard. It'll be a little bit hard, even though it's a simple case. So don't get frustrated if it takes a while. So you may struggle with it, but it should look cool if you get it working well. So consider it a great success if you get your balloons bouncing reliably and looking nice. All right, so that's going to be it for exploding balloons on the stream. We're going to move on in a minute to the next project, which will be the evolving picture project. If anyone has any questions or concerns about the exploding balloon project, let me know now. I'll hang out for a few minutes before I go on to the next one. All right, so I'm going to make a new folder. Call it Evolving Pictures. All right, let's start talking about the evolving picture game we're going to do. So the basic idea is we are going to have equations that draw images. So you can imagine a really simple case might be something like this. Sine of x plus y, and that's going to equal the intensity of some pixel. All right, so we'll call it P of I is the intensity. Oh, that's pi. That's too confusing. We'll just call it the intensity or color of a pixel equals sine of x plus y. So if you imagine in your head what this would end up looking like, the intensity along the x-axis would of course be sinusoidal across the image, and then as you go down the image, it'll get brighter. So you'd have something that like gets brighter as you head towards the bottom, but also gets brighter and darker as you go along the x-axis. Right? You can get different patterns. Right? Or you could have something where the intensity just equals x, right? And that would be something that starts out dark on the left side and gets brighter and brighter until you get to the end of the image. So you can imagine as you add more operations here, like multiplication, division, cosine, tangent, you can start getting some pretty interesting patterns. And you can build up these equations arbitrarily large as you want to make different kinds of images. So this idea is what we're going to use to draw our image. And then we're going to use a genetic algorithm to evolve these equations to make them look as cool as you want. So we're going to make a little app that'll look something like this, where we're going to show a bunch of thumbnails. Maybe we will do 9, maybe we'll do 12. So when you first start it, we'll generate some random equations, and we'll draw each of those random equations in these thumbnails. Right? There'll be crazy different things going on in each one. Each one will be random and different. And then the player or user will pick some number of them that they think are the best looking, that they think are their favorites, right? So they might pick 1, 2, and 3. And then we will use the equations that they picked and use the genetic algorithm to combine those equations in some clever way and maybe mutate the equations a little bit to make a new set of 9 thumbnails. And then you can repeat that process, and then The idea is the genetic algorithm will keep evolving the equation to make pictures that the player actually likes looking at. And then along with this, we're going to add some other features like being able to save the equation to a file, load the equation from a file. So if you get one that you really, really like and you want to save, you'll be able to save that equation to a file and then reproduce it later, right? And maybe draw like a full screen version of it if you want to. Okay, so that is the basic idea. So the first thing we need to do this is be able to draw pictures with an equation. And we need to be able to kind of modify and manipulate those equations in arbitrary ways, right? And create random ones, right? So it's easy enough to write an equation. We're all kind of familiar with what that would look like, right? How do we represent this in code? So it turns out there is a commonly used way to do this that's really nice. And the idea is you represent it as a tree. Okay, so this equation here, sine of x plus y, could be represented by a tree like this. You have one node that is a plus operator. Now, a plus operator has two children, right? You operate on the left side and the right side. And on the right side is just y. And on the left side is a sine operator. And a sine operator has one child. And in this case, the child is x. So this is the tree that would represent this equation. Now this has a lot of nice properties. For one, if we want to actually compute the result of this equation, all we have to do is walk the tree. And if you remember from our episode where we did the binary tree text adventure, where you could choose yes or no, it's very easy to do a recursive function that walks a tree and visits everything in order. So to evaluate this tree, we would say, okay, to evaluate plus, first we need to evaluate the left side of plus, right, which is sine. And to evaluate sine, we compute sine of x. Then we get our result back up here. Then we need to evaluate the right side, which is just y. And then we add the results of our evaluation of the left and the right. So it's a very easy recursive thing to compute an answer. The other really nice thing is it's really easy to take this tree and spit out text that is easy to read or use in other ways. Right? We can do the same kind of thing with evaluation. We can do a in-order tree walk to spit out text that might look something just like we wrote above. Right? Or we can even write out valid Go source code. Right? We just have to remember that we need to call math.sign whenever we have a math operator. Right? Then we've got valid Go source code, which is pretty interesting. Like maybe our, if we wanted to improve performance, right, we could spit this out as Go source code, then compile it, and then render our image or something like that. The possibilities are kind of endless. You could output valid shader code and then render these things on a GPU. So this kind of tree is called an abstract syntax tree, and this is actually how compilers work. When you compile your Go program, it goes through a step where it's parsed the raw text that you type that looks something like this, and it creates an abstract syntax tree representing all of your source code, and then it goes on to the step of optimizing it and turning it into machine code after that. So this is a really powerful thing, and you'll hear the phrase abstract syntax tree a lot, and it sounds confusing and complicated. It's really not. It's just a tree. It's not a binary tree. You can have any number of nodes that lets you represent expressions and statements. In this case, we're just going to represent equations. Okay, so how do we do this in code? Let's give it a try. So I'm going to make a separate file just for the abstract syntax tree part of this project. And I'm going to call it APT for abstract picture tree for fun. So we'll make a package for all of the tree related stuff. So one way you could do this in code is you could make something like a node struct. And your node, in this case, because we're not just a binary tree, right? We can have some operations will have one child, or some nodes will have 0 children, like our x and y will have no children at all. Our sign operation will have 1 child, plus operation will have 2. We can imagine other functions that have more than 2. So the number of children here would be something like an array of nodes, right? And then we would need some kind of ID to identify what our operation is. So like operation could be an integer. And then our code would look something, when we're working with this, we'd have to have something like a switch where we look at what the operation is, right? And we'd have different cases. If it's the plus case, then we're going to do, addition. If it's the minus case, we're going to do subtraction. So this approach would work. It is one way you could do it. But we're going to do it a little bit of a different way that will be nicer in some ways. So we're not going to have an array. We're going to make some heavy use of Go's interfaces to represent this stuff. So we've basically got many different operations that we want to support for our images. We're going to want to do plus, divide, multiply, subtract, sine, cosine, atan. We can even throw Perlin noise in there, or simplex noise in our case, and so on. But there's basically different categories of these things. We're also going to have x, y, and constants, right? So we're going to make it possible for our tree to just have like a number in them, right? This could be, times 5 or something. So we've got lots of different operations, but all of them fall into one of a few categories. That could be leaf nodes. So we're going to call our nodes like x, y, and constants leaf nodes because there's no more operations under them. They're always the bottom of the tree. There's always going to be leaf nodes. That's where it ends. So we've got leaf nodes with 0 children. We've got single node things like sine, cosine, and then double node things like plus, minus, etc. So let's make a type for each of those categories. So we'll make a leaf node struct, and that'll actually have nothing in it at all. And we'll make a single node struct, which just has 1 child. We can call it child. And it'll be some kind of node, right? This will have a left child and a right child. Okay, and the compiler's not happy yet because we haven't defined what a node is. So let's do that. So we're going to make node an interface. Now we talked briefly about these when we were doing the balloons because in order to sort things, you need to satisfy the built-in Go sort interface. So an interface is a contract. An interface lets you define a set of functions. So in this case, we're just going to define the eval function. So eval is going to be the function that when you give it a node of a tree, right? If you give it the plus, it'll compute the answer. It'll compute the full result from that node of the tree. It'll figure out sine of x, add that to y. So any node that we have, whether it's a plus node, a sine node, an atan node, has to provide an eval function. And if it provides an eval function, then the plus node or cosine node or whatever can be considered a basic generic node. And that will let us put all these different kinds of things, the plus and the minus, the x and the y, inside these trees, right? Because as long as it's a node, and if it will be a node if it provides an eval function, then it can go in there. So let's actually build a couple of simple ones. So we will create a plus operator. And we'll call all of our operations, start them all with a OP for operation. So we'll make op plus a struct. And it's going to have, we're going to use struct embedding to build this. So instead of giving it a left child node, etc., we're just going to say operation plus has a double node, right? So it is a double node. And that's going to be useful later on, as we'll see. And then we're going to make an eval function for it. Okay, so our eval has the same signature as the interface, which means even though this doesn't do anything, we already have satisfied the node interface. Now what we want to do is, this is where we use recursion, and that actually makes it surprisingly easy. To evaluate any given plus node, which would be just like this, all we have to do is evaluate the left child. So we just call its eval function. Then we do plus because we're the plus operator. And then call eval on the right child. Undefined x and y. All right, and that's it. So we have defined a plus operator, which is now a valid node because it satisfies the node interface, and it can compute the result. So at this point, we could build a tree as long as we only used plus operators. But we're going to need more than that. At the very least, we're going to need the x and the y. So let's make an x and y. So we'll do op x. And that's going to have, or be a leaf node. I think we could actually just do it like this. Make that as equivalent. Do x and y. So evaluating the x operation is really simple. You just return x. And evaluating y is really simple. We just return y. Oops. Why is this unhappy? Oh, this should be func. Okay. So at this point, we should be able to have a tree that can add x and y. So let's see if we can give that a try. So we're going to make a new file. It's going to use this package. Then we need to import this. Let's see. Oh, we need to make a directory for that. So let's make a new directory, apt. We're going to move apt.go into apt. All right, cool. Okay, so let's make can we do that? Oh, this should be oh, that's okay. Y plus too many values. These need to be pointers. Okay, so we're setting up a plus operation, and we're giving it a left child of x and a right child of y. So let's try plus.eval 5, 2. Print it out. Oh, got to import format. Times. Did we do times? No. Why is that 10? Let's print x and y out in here. See if that 5 and 2. They're both getting 5. Oh, because I gave it 2 X's. Simple enough. Thank you. Paratrier caught it in chat. Thank you, Paratrier. Okay, so we can add numbers. This is huge. So let's add let's add some complexity. Let's add the sign operation because that will be a different type of node. It's going to be a single node, and we'll make sure that works. So we'll do type op sign. All right, and we'll use struct embedding. Again, that means that op sign will get all the things that a single node has automatically. And we're going to satisfy the node contract. And then this will be we'll take the single child, call eval on that, and the result of that, we compute the sign and return it. We'll need to import math to get the sign. Okay, so again, we're using recursion. We take the one child of our sign operation, we call eval on that. Whatever result we finally get, we then compute the sign of that and return it. So let's go back to here, make this a little more complicated. We'll make this turning the sound back on. Is it back? We're back. So we'll make this equal to a op sign, and we'll say sign.child equals x. Okay, so now we're going to have, we should have sign of x plus y. All right, there we go. Let's get rid of this extra debug stuff. Now we have an unused format. Okay. So now we've got to the point where we can do exactly what we drew here, right? We're doing sign of x plus y. And so you can see here how we can add any number of operations we want. All we have to do is define a struct with the name, pick the correct type of node to embed based on how many children the operation has, 0, 1, or 2, and then implement an eval function for it. Right, so at this point we're set up to do any number of operations we want to do, right, including crazy stuff like perlen noise. So before we do that, let's show another cool feature that we can do, which is the ability to print these things. So there is a sort of convention in Go. If you want to output a string for something, you call the function string. So we are going to give our node interface such a thing. It will have a string function that returns a string. So now at this point, now that the node interface requires both of these functions, not all of these things are satisfying it. Plus is no longer a node because it doesn't have a string function. So we got to give it one. Let's move op sign. Let's keep the functions with their structs. So let's quickly do a string for each of these. So all you have to do here is pick some syntax you want to use. And then again, use recursion. Right, so when we print out the sign operation, we'll print out sign, parentheses. Then we print out its child tree, and then close parentheses. And then for plus, we can do it like this. Right, child capital. Then our two leaf nodes are really simple. And if you remember from the recursion talks earlier, we always talked about base cases. The leaf nodes are our base case. That's where we will always stop doing recursion, because there is no deeper you can go. Just return x. We'll just return y. So now we can go back here. And because we now implement a string function, format.println, I believe, looks for that string function to satisfy its own like printable interface. I don't remember what they call it, but I think it will know to use our print function. Let's see. Yeah, there we go. So now we're printing out sign of x plus y. And you can see how we could make this valid Go code really easily. Now that's valid Go source code that you could use somehow. You could recompile it. But what we're actually going to use, the format we're going to use for this, is we're going to use something like a Lisp type syntax. So if you've seen Lisp before, there's lots of parentheses. But the benefit is it's very simple to parse, and everything works the same way, right? So the syntax we're used to, we're very much used to this because we do it in school, right? Where plus is an infix operator. It goes in between the two things it operates on. But we're also used to functions like sign or polynoise, where we state the operations first and then list the things it's going to operate on after, right? And that's prefix notation. So we're going to make everything prefix notation in our little scheme here. And the reason we're going to do that is it will be easier to parse when we want to be able to load up our equations from a file. We're going to be able to save these to a file or paste them in and then render them. And the Lisp syntax will make it much easier to parse. So this then just turns into a paren, a space between what we're operating on, close paren. So let's see what that looks like now. Let's be maybe consistent with our spaces. Okay, so this has the same meaning, just that we have a plus operation that then operates on sign of x and then operates on y. All right, and this might even be valid Lisp code in certain dialects of Lisp. We could certainly make it that easily. Okay, so that is the power of an abstract syntax tree, is it's really easy to evaluate things and print them out in different ways, right? We've just gone from kind of normal human syntax to Go syntax to Lisp syntax with just minor changes. And we could leave all those versions in here if we wanted to. All right, any questions so far about where we're going with this? So at this point, it might not seem like it, but we're very close to being able to draw pictures with these equations, because already we can do the math. All we have to do is take the numbers that we get out of these trees and set them equal to pixel values. So I guess what we can do, we got 10 minutes left. We can start building up the SDL2 code to draw these pixels with. And we can probably just rip the necessary things we want out of our balloon code. Maybe we can even just copy all of this and then rip things out. That might be the easiest way. So let's give that a try. So I'm just copying and pasting everything from balloons2.go. And I'm going to start tearing things out that we don't need. I'm going to leave these here because we might make use of them if we do sound. Get mouse state could still be useful because we're going to want to be able to click on buttons. We definitely will not have any more balloons. Let's get rid of all the balloon stuff. Not going to draw any balloons. Probably not going to set pixels, but we'll leave that for now. Probably not going to be loading images because we're going to be drawing them with equations, not loading balloons. Don't think we're going to use any of this either, so let's delete the lerps and the gradients and the clamp and the rescale and draw. Okay. Then let's rename this to Evolving Pictures, or whatever name you like. We'll keep the audio code in just in case we want some sound effects. Well, no, let's comment this out for now because we're not going to load any WAV files for sure. So we'll comment out the audio section, bring it back later if we need it. Okay, there's no clouds or balloons. We can keep the touch events in there. That might be useful. Normal balloons. No more drawing balloons. Okay. And no more cloud texture. All right, let's see. We got 7 minutes. Let's see if we can render a simple equation or not. So let's get ourselves a simple tree again, just before we start our loop here. Let's do x op x, y is equal to op y. Sine and plus equal to op plus, just like we had before. So sine dot child x and we're going to need to re-import this. Delete all the unused imports and add the one we are going to use. Why isn't this happy? Following pictures / apt. Oh, use the dot notation, so I don't want to have to type apt before everything. These should all be pointers. Capital right child. Okay, I'm commenting out previous mouse state because we're not using it. Go doesn't let you not use things. Okay, so now we have our sine of x plus y. So we're going to want to compute a bunch of pixels for it. How should we do that? So we're going to want a picture that turns a tree into a function that turns a tree into a texture. So let's set something up for that. I might go a few minutes over here, but it'll be worth it to see some stuff on the screen. So we're going to have an abstract picture tree to texture. And we'll just start with we're going to make it black and white to start with. We're just going to take it in one node. Take it in width and height, which will be ints. We need a renderer. And we'll return an SDL texture. Okay. So we're going to try to treat our have all of our functions kind of be between -1 and 1 eventually. So we're going to want to scale that to our 0 to 255 for our colors. So we're going to have a scale and offset to do that. We'll need to make our pixels. So we'll need an array of bytes. Width times height times 4 bytes per pixel, red, green, blue, alpha. We'll start our pixel index at 0. And we're going to design this so we'll be able to draw our pictures at any size we want to. So if we do it at 200 by 300, it'll look the same as if we draw it at 2000 by 3000. It'll just get more and more detailed, but it will be the same picture. Okay, so our y so we're scaling the integer value of y by the height of our texture. We can pull y outside of the x loop because it will never change inside the x loop. So we do the same thing for x. Then we'll get our colors. We're going to say r. So color is equal to node.eval x and y. All right, so we get the floating point x and y values we compute, pass them to nodes.eval. That will do the recursive evaluation of the whole tree and return back some floating point value c. And then we're going to say pixels. All right, we're going to take our floating point color value, which we're going to eventually will be scaled from -1 to 1, and scale that into a byte. And for now, if this is not between -1 or 1, it's just going to overflow. It'll be okay. We'll get something once it gets cast to a byte. And then we'll do this for green and blue. And then we'll do one more. We're going to skip alpha. We're not going to use alpha for this. All All right, and we already have our pixels to texture function that we made before for our balloons. So once we have our pixels, we just call that and return the texture that we get. Okay, APT to texture. So we should be able to say text is equal to APT to texture. Give it our node, give it our size, we'll do full screen. Pass it our renderer. Not node, give it plus. Okay. Then we just need to copy that to the renderer in our game loop. Let's see what happens. All right. So you see now we've turned our equation tree into a picture. It already looks mildly interesting, even with just one color. Someone in chat says Golang trend. Is this the trend line for Golang? The popularity? So for now, we're just doing the single color. What we're going to end up doing is have a separate equation tree for red, green, and blue. And that'll let us mix things together to make all kinds of crazy images. All right, so this is a really good start. We have the basis for what we need. We know it's going to work. We can add more and more operations to this. When we add operations, all we have to do for now is create an eval function and a string function. We're going to start doing some more things because these trees we're going to need to be able to manipulate. We're going to need to be able to add operations to a tree in an intelligent way, like randomly, so we can make random equations. And we're also going to need to be able to do operations that let us do genetic algorithm stuff. Like we might want to take a node from one tree, cut it out, and paste it into an area of another tree, and have that all work. So we're going to be expanding this quite a bit to be able to do those things. And we'll be adding some more operations so that our pictures get more interesting. So that'll be the next steps coming up. All right, out of time. I'll stick around for 5 minutes in case anyone has questions about this stream or previous streams, anything at all. All right, while I wait for questions, I'm going to do one more thing just for fun. Now we got some color. Jack Mesh in chat asks, do you program on Unity or Unreal by any chance? I have done some hobby projects in Unity, so I have a little bit of familiarity with it. I've never really done anything with Unreal Engine. Unity is pretty nice for being able to do certain kinds of games really quickly. One of the fun things about it was like there was some 12-year-old kid in the forums asking questions about how to spawn infinite zombies. And I thought there'd be no way he'd be able to do it, but he spawned infinite zombies, which is pretty cool. But it can be frustrating to work with Unity if you're trying to do something a little bit weird and it doesn't support it, and you have to figure out how can I make Unity do the thing I want to do? How can I make it perform well? You've got that big editor that loads up whenever you want to use it. So for certain kinds of projects, it's not a good choice. And The C sharp that Unity uses used to be really ancient and have extra performance problems on top of what you would normally have with C sharp, but that's been rapidly changing. It's Mono is owned by Microsoft now, so Unity is free to start upgrading the C sharp runtime a lot. It should get pretty good because the latest C sharp runtime is very solid. Like I wouldn't expect a Go program to necessarily be faster than a C sharp program uh, in general. It just depends. Any other questions? All right, guys. Feel free to play around with this and add your own functions and stuff. We're going to build up on this next time, increase the complexity of the things we can build, and start adding some of the operations to add things randomly to the tree and manipulate the tree. And then after that, we'll start building the interface to be able to show multiple multiple pictures at a time, and then we'll start doing the genetic algorithm on top of it. All right, good night, everybody.